The last thing we did, and you finished and we reviewed online yesterday, was that beautiful investigation of inverses of functions. Okay, so we took various functions and we reflected them across y equal x to get their inverses. Their inverses may or may not be functions. So what we were discovering was the graphical representation of what it means to take the inverse of a function. The graphical representation for taking the inverse of a function is, in fact, you are reflecting the original given function across y equal x to get the image. That's what it means to geometrically take the inverse of a function. Now, we also talked about relations versus functions. So if you remember, a relation, oh, my pen is having issues again today. A relation is a mapping of input values to output values. It is a rule. Some very special relations are functions. So not all relations are functions, but all functions are relations.
Say it again.
Somebody say what I just said. Right. So some very special relations, mappings of inputs and outputs, are functions. Which ones are functions? Well, for every x, there is only one y, right? For every input, you can have only one output for that relation to be a function. So sometimes when you take the inverse of a function or a relation, its inverse is not a function. Now, algebraically, what did we notice when we looked at tables of values? Well, if we had the input of the original relation, what happened to that input? That input became the output of its inverse, right? The output became the input of the inverse relation. So what is happening? The domain and the range are changing. The domain of the original relation becomes the range of its inverse. The range of the original relation becomes the domain of the inverse. So if you have a graph, you can make a table of values and graph the original relation, and to obtain the graph of its inverse, all you have to do is change the x and the y values, plot those points, connect them, and you have its inverse.
There's going to be graph and
Quite possibly.
Or
What did you say?
you're going to have to graph like a function.
Okay.
Is it true that only odd or like odd degree functions have like a defined inverse? Or no?
No, they all have an inverse, but their inverses may not be functions.
Yes.
Yes.
So
Yes.
only odd.
Well, and I wouldn't even go, I would be careful with that. Yeah. All right. So what happens, and boy, I'm giving, I hope you're paying attention. If I were to give you two functions, two rules, how would you determine if they were inverses of each other without actually finding the inverse of each and seeing if they're the same equation? Well, to verify two relations are inverses of each other, we must show this. We must show that f of g of x equals g of f of x equals x. So the composition in both orders, so given two functions, so if we are given f of x and g of x, we're given two functions. To determine if they are inverses of each other, we take the composition in both orders, f of g and g of f, and the compositions must equal x. So we have to show, again, we need to show f of g of x equals g of f of x equal x for all domain values x for both f and g. Does this make sense? If I ask you to verify or determine if two given functions are inverses of each other, you must take the composition in both orders, f composed with g, g composed with f. They must both equal x. If that is true, they are inverses. Okay? So let's do an example. Let's say we want to verify f and g are inverses of each other. Again, I do not want you to just calculate the inverse of f, calculate the inverse of g, and see if you get the other function. I want you to state we need to show this. Okay, so we need to show each of these should equal x. If each of them equal x, they are inverse of each other. So let's go ahead and do that, okay? Because we need to be able to... Why are you not erasing, you pitiful thing? All right, so let's go ahead and do that. So I'm going to start. Remember to take the composition. I'm going to start with the big function outside. So I'm going to start with f of x. I'm trying to figure out what this equals. I'm going to start with f of x, which is 3x plus 2. Then I'm going to input into f g of x. So everywhere I see an x, I'm going to substitute in, g of x. G of x is x minus 2 over 3. So then I'm going to simplify. And I'm going to be left with, for the composition, f of g of x, what am I going to get? Yeah, because this is x minus 2 plus 2, so it's x. Don't get excited. We're halfway there. So now I'm going to start on the outside. With g of x. And everywhere I see an input, I'm going to substitute it with f. So I have g of f of x. F of x is 3x plus 2. So then if I simplify that, what do I get? Oh, look. So g of f of x equals x. So since f of g of x equals g of f of x equals x, for all x in the domain of f and g, then f and g are inverses of each other. So you have to always state what you need to show. Then f and g are inverses of each other.
When you were like x
Then for all x in the domain of f in the domain of g,
Do we have to write that, or can we just say since f is
if you've stated it up here, then you can just state this and say they're inverses.
where would we have stated the other thing?
At the very beginning, you always state what you're showing. We need to show f of g of x equals g of f of x equals x for every x in the domain of each. You have to state that. You can't just start doing some algebra. What are you showing me? Show it to me, and then from what you've shown me, draw the conclusion.
So if x, e, e, f, then y, here.
Since f of g of x equals g of f of x equals x, I know they're inverses. If you want to be specific for all x's in the domain of f and the domain of g, then f and g are inverses of each other. Does that help, Jonathan? Okay.
But we only have to say since f of x
Yeah.
equals, or f of g of x equals g of f of x.
Yeah.
Okay.
But you must state this. You are going to lose a lot of points if you don't state that. All right. Now, as Jonathan pointed out, I may give you two functions. Look, I gave you two functions. How exciting is this? So here are my two functions. I have f of x. I have g of x. Those were the two I just gave you. I want you to graph each of them on the same Cartesian plane. So I could go ahead and say, all right, let's go ahead and do for function f. And then I can easily get g. So I can make a table of values. I can choose some x and some y values. Let's say I substituted -2, -1, 0, 1, and 2. I could get my corresponding y's just by substituting values of x into this equation. I have an equation. So I could plot some points. This would give me -4, -1, 2, 5, and 8. I'm going to plot that. Or I could just plot the y-intercept, rise 3, and run 1. But I'm going to be careful on the test, right, to graph this nicely. I'm going to do my best on this iPad. Okay. And I'm going to label that as f, because I need to know that's my original function. Now remind me again graphically what it means to take the inverse of a function. What am I doing graphically? Geometrically, what's happening?
Reflecting it across the line, y equals x.
I am reflecting it across y equal x. Absolutely correct. So do you have to show y equal x? No, but I like to see it. Heaven help me. And the quick and easy way to do it, knowing the relationship between a function or a relation and its inverse, is I could just interchange these, correct? And I could get the point -4, -2, -1, -1, 2, 0, 5, 1, 8, 2. Or I could just rewrite this if I really wanted to. Right, that works too. -4, -2. Oh, well, we knew those points were gonna, well, I'm gonna just make a big point there because we know it should be there. 2, 0, 5, 1. So do you see, all you have to do is get a table of values. Oh, heaven help me with this graph. Do you see what I've done? This is what you have to be able to do on the test. Given a function, graph the function, find the inverse, graph the inverse. I'm sorry? What? What did you say, Jonathan?
Easy money.
Easy money. All right, now, one thing I do want to point out, because we have to be familiar with notation, is that, oops, this does mean inverse, right? So I know we've been working with negative exponents, right? But in this case, this is a function raised to that -1 power. So that symbolically represents the inverse, right? If I were taking the entire function and raising it to the -1 power, that is something different. This is not the same thing. Do you see why this is not the same thing? Don't get confused.
It's not f of x.
It's not f of x. So this is technically a y value, right? This is a y value. A y value is just a constant. An output is just a constant, right? If I take a constant and raise it to the -1 power, then we know how to write that without a negative exponent. It's 1 over that number to get rid of that negative exponent. But if you have a function, a rule, raised to the -1 power, that means the inverse. Don't get confused. Okay? So let's talk about the quick and easy way, given an equation, given a rule, how to write its inverse. So let's say you are given this same exact function, f of x equals 3x plus 2. I can rewrite that as y equals 3x plus 2. Now, I know the relationship between a function and its inverse is the domain and the range are changing. So I can literally come in here and change the domain and range to x equal 3y plus 2. Do you see how I just interchanged? And then erased it. How I just interchanged my x and my y. That's all I did, because I know that that's what it means to take the inverse. The domain of the original becomes the range of the inverse and vice versa. Now, what do I do with this? I solve for y. So to solve for y, oh, come on, easy. Easy money, as you say, Jonathan. And then I would represent that as f inverse. Oh, we kind of all, that was supposed to go up here, but we did it. Now, how could I check? How could I check that this is in fact the inverse? I did it correctly? Exactly. But in this case, our G is f inverse that we found.
On this test,
Mhm.
would you just be able to put this formula at the top?
All right. Now, we also talked about, given a relation or a function, if we took the inverse, is the image, the result of reflecting it across y equal x, also a function? Well, one way we determined if an original graph was a function was by looking at the vertical line test. If you look at that original function and it also passes the horizontal line test, then its inverse is also a function. So that's a quick way to determine if the inverse of a relation is a function. So let's use the horizontal line test to determine if the function itself has an inverse. Can anybody, well, let's go ahead. Let's look at y equal x cubed. We should know that parent function. We should be able to graph that parent function ever so quickly. So that's y equal x cubed. Now, if I wanted to find its inverse, I could interchange the x and the y, and I could solve for y. And I would get y equals, is it just the cube root of x, or do I need a plus or minus? Just a cube root, because the root index is odd. Good. So if I called this f of x, then this would be f inverse of x. Now, I could plot points, right? And I could graph its inverse, but what can you tell me immediately? These are hideous. That's a hideous graph, but you get it. If I were to look at the original function, the red one, I know it's a function, it passes the vertical line test, but is its image going to be a function? Well, does it pass the horizontal line test? Yes, it does. Now, if I were to give you the parent quadratic function, hideous, and call that f of x, is its inverse also a function? No, it doesn't pass the horizontal line test. Right? Its inverse is not a function. And we could interchange points and we could graph that as well. Now, these functions.
Wait.
Yes.
Yeah, the inverse has to be like function.
No, it doesn't. That's the whole point. The inverse may or may not be a function. One way to tell from the original.
It still has an inverse.
It has an inverse, but the inverse may not be a function.
Okay.
Very good. Now, these special little functions that do pass both, well, the vertical and the horizontal line test, meaning each input has only one output, but each output has only one input, are known as one-to-one functions. One-to-one functions are functions that pass the vertical line test because they are in fact functions, but also pass the horizontal line test, so that means that their inverse is also a function. Okay? Say that again.
Like if they're both, then the inverse is automatically a function.
If it passes the vertical and the horizontal line test, the original relation is a function, and so is the inverse. Yes. Well, it's just like the vertical line test. The horizontal line test says, can I draw a horizontal line and pass through the graph more than once? If it's one-to-one, meaning if the inverse of the original relation is a function, then it is one-to-one. Okay, so I could give you any function, right? I could give you any function. Can anyone give me an example of a function that is one-to-one? Anybody think of an example of a function that's one-to-one? One-to-one. Passes the vertical test and the horizontal line test. Think of our parents. Yes. And I'll do a quick sketch. Right? That's one-to-one. It passes the horizontal line test and the vertical line test, one-to-one. Can anybody think of a function that is not one-to-one? Y equals x squared. Not one-to-one, right? So horizontal line test tells you if it's a function. Vertical line test tells you if the inverse is also a function. Now, if I were to give you, and we've done this so many times that you should almost know this by heart, if I give you the parent quadratic function, you should be able to graph that with ease. So I'm going to call that f of x, and I would label that. And if I wanted to graph its inverse on the Cartesian plane, well, we said its inverse is not a function. So if I were to reflect that across y equal x, I'm going to get this, right? It's not a function. Now, the domain of the original function is what? That's right. And its range, so let's go ahead and state that. The domain of the original function is negative infinity to positive infinity. What is the range of the original function? 0 included, 0 to infinity, right? That's our original function. Now let's look at let's look at the inverse. Okay, so technically the inverse doesn't exist. It's not a function. So this would be the inverse. And can you tell me about the domain of the inverse?
Included 0 to infinity.
And the range?
Negative infinity.
And we should know that because of this relationship, right?
So for the domain of the inverse, could you just do like d of f to the negative first?
Yeah, but technically it's not an inverse function. Yes.
Oh, okay.
Now, if I were to impose some domain restrictions on my original function, so what if I said I want to look at f of x equals x squared, but only when x is less than or equal to 0? So I'm starting with this. So if I'm starting with that, I'm only looking at this. Right? Is that one-to-one?
Yes.
It sure is. And its inverse would look like this, right? For kicks, what is the domain of f?
Negative infinity to 0.
Okay. And what is the range of f? Okay. And we would pay attention to whether that's included here, right? And what can you tell me about the domain of f inverse? And the range of f inverse? Okay, so hopefully you're noticing this relationship. Now, I could also restrict it in a different way. What if I only look at for when x is greater than or equal to 0? Then I'm really only looking at this part. Is that one-to-one? Yes, it would be this, right? And we could do the same thing stating the domain and the range. So while each of these little restricted pieces are one-to-one, the original is not. The original parent function is not. All right, that's all the new stuff. Let me, I put together a few little problems here after I wrote the test. So let's, shall we do these together?
Are those in the packet?
No, they're not, because I wrote them this morning after I finished writing the test. Okay, so here we go. Let's say we are given these two functions, because you will be given two functions on the test. Okay? Now, are there any domain restrictions on the first function? No. Are there? And what kind of function is that? Linear. Are there any domain restrictions on the second function? No, because what kind is that? It's quadratic function, right? The parabola opens up, parent function's been shifted down one. This is all stuff we should be able to say. Now, what if I ask you to find f of g of 4? Well, you sure could take the composition f of g and then substitute in 4 for x. But is there a faster, easier way to do this? Yes, I could first evaluate g of 4. Could I not? Okay, let's evaluate g of 4. So I am eventually going to do f evaluated at whatever g of 4 is. G of 4 is 4 squared minus 1, which is
16 minus
right? You with me? Then I'm going to substitute 15 in there. And I'm going to evaluate f at 15. F at 15 is what?
10.
So this whole thing equals 10. Quick and easy. If you know how to do these, they're easy. Now,
Still make it as a composition input.
well, let's see what happens if that works. So if I want to compose f with g and do it that way, let's go ahead and do it that way. See, ooh, we said it was 10. So f composed with g, I'm going to start with f on the outside. And I'm going to compose that with g. G is x squared minus 1. So f composed with g of x is what?
X squared minus 2.
Okay, what is x? So f of g of 4 is 4 squared minus 6, which is, so if you want to do the composition, you go right ahead and then substitute in the value for x, or you can work from the inside out. Make sense?
Yeah.
Okay, what operation am I asking you to perform in B? Multiplication. So make sure you know the difference between composition and multiplication. Know when to do each. So I could multiply f times g and then substitute in 0. Or do what? Oh no. Is this not f of 0 times g of 0? So I can substitute in 0 for f, 0 for g, and then multiply those two numbers together. Or I could multiply f times g and substitute in 0 for x. Either way. So let's do f times g. F times g is what? Tell me what it is.
It is x cubed minus 6. Oh wait. Minus 5x squared minus x
Plus 5.
plus 5. Yeah.
Right? And then if I substitute in 0, that gives me 5. Okay, let's do it the other way though. F of 0, 0 minus 5. G of 0, 0 squared minus 1. Negative 5 times negative 1. Doesn't matter which way you do it. One way's faster than the other. Less room for error. Make sense? Okay, what if I give you this table of values and ask you to utilize this table of values? And I may give you the table, this information in many different ways. So let's say you're given it this way. You are being asked to find f of 2 and then subtract 3 times g of negative 1. How am I going to do that? Okay, so I'm looking for f of 2. What is f of 2?
8.
Do we see how I evaluated f of 2 to get 8? Okay, then that's minus 3 times g of negative 1, which is, does everybody see how I'm getting this information from the table of values? Miles, you're looking a little, I don't know how to describe that.
I did it.
Okay, so then I have 8, what?
Plus 12.
Plus 12, which is, okay. What are you being asked to do in the next one? Composition. So you're being asked to find f of g of, no, I made these up this morning. So what am I going to do here? Okay, so I'm evaluating what first?
G of X.
G of 1. What's G of 1? Okay, so then I need to evaluate, oops, F at what? 0. F of 0 is what? F of 0 is 4. So if you understand what you're being asked and you can interpret the information given to you, these are fast. So while you may look at that test and go, oh my gosh, there's so many problems, there's like 17 problems. Look how fast these are. If you know how to do them, these are fast. If you don't know how to do them, God help you. Okay?
Really good. What is like the FOG?
Somebody explain what this means.
So the O is like a multiplication.
No, don't say multiplication. It's not multiplication. It's composition.
G and put it where the X should be.
It's composition of two functions. That open circle means composition. You're composing.
So FOG is the same thing as F of G of X?
Yes.
Yeah.
Yes.
This is like I gave you the one, and you can substitute the one.
So you do have to know.
G at 1 is 0, so you just substitute F of G of 0.
You do have to know that this notation means composition, and that's the same thing as this.
Gotcha. Let me write that down.
That's important. It's all over the notes. Are there any questions? Any questions online from anybody online?
All good on my end, so